Which cycloalkane is the most stable? We can see that these are all substituted cyclohexane rings. To find the stability of the molecule, we can look at its chair conformation, which is this structure right here. The chair conformation is the most stable conformation of cyclohexane because it minimizes torsional and angle strain and maximizes hyperconjugation. The substituents of the chair can either be equatorial, pointing outwards, or axial, pointing up or down. The green substituents represent equatorial positions on each carbon, and the red substituents represent axial positions on each carbon. The most stable conformation usually prefers the most equatorial substituents because it avoids steric crowding. To convert from the flat hexagon to a chair conformation, you want to first make sure the largest substituent is in the equatorial position. This way, you minimize steric strain. Designate that as carbon 1 so that you don't mess up when counting. Second, draw out the other substituents relative to the first substituent. All wedge substituents should be up and all dash substituents should be down. Be careful when distinguishing between equatorial and axial and up and down. Finally, count to see how many equatorial positions there are in a final product. Let's try it on the molecules we have. In A, we have a wedged bromine, so we can draw the bromine up in equatorial on this carbon right here, labeling it carbon 1. Then labeling the rest of the carbons, we can put the methyl group at carbon 3 down, which will make it axial. Then we add the methyl at carbon 5 up, which will make it equatorial. Therefore, we have 2 equatorial substituents in total. In B, we have a dash bromine, so we can draw the bromine down in equatorial on this carbon and label it 1. Then we can label the rest of the carbons and put the methyl groups in. Carbon 3 has a down methyl group, making it equatorial. Carbon 5 has an up methyl group, making it axial. We have a total of 2 equatorial substituents. In C, we have a dash bromine, so we can draw it down in equatorial. Labeling the carbons, we have methyl down in equatorial at both carbons 3 and 5, giving us a total of 3 equatorial substituents. Finally, in D, we have a wedged bromine, so we can draw it up in equatorial at this carbon. After we label the carbons, we can add the methyl groups down, but in an axial position at carbons 3 and 5. Therefore, we only have 1 equatorial substituent in D. Because we have the most equatorial substituents in C, that is our most stable cyclohexane.